Why, hello, mathletes. Welcome to Unit 7. You should have received the Unit 7 quadratic functions packet. If you go through it, we have a total of, I think, 6 lessons. Seventh day would be review, eighth day will be the test. This is our second to last full unit, and most of this will go on to the fourth quarter. The third quarter ends on April 12th. So today I'm not going to hand the test back because I'm not here, but I'm going to introduce you to what a quadratic is. And a lot of this is going to be out of your calculator. So if you have your own, that's great. If you don't have your own, you're going to need to find a way to borrow one or use one during a study hall or something of that nature. So I'm going to start right off. Day one, page one. We're not going to do all the tasks in this, but this is giving us a little heads up of what's going on. So we've got the Super Pyrotechnics Inc. company that offers professional firework displays. And they have been hired to put a display on for the town of Algebra's Pi Day celebration. Awkward pause. Excellent. So the main thing that we're going to need to know is we are modeling the behavior of something with this function. Okay, this is function notation, so they've got h of t is like my y value, and then everywhere there's a t, that's the same thing as using as an x. Okay, so right now what I want you to do is I need you to pause the video and plug that into your calculator. Okay, and what's important is make sure that you're using the negative key. It's smaller than the minus key. Okay, so I put that there, and then we're going to go second graph. All right, and this is showing us the behavior of a firework after it's launched t seconds. So t equals 0. This is like my initial value. So the fireworks are being shot from 3 feet off the ground. Okay, and we don't really care about negative time, so that doesn't make any sense. So if we're talking about domain, we want to start with 0 and move forward. And I'd like you to fill in the table from 0 to 11 from your graphing calculator. Now, I'm really hoping that you did this on your own. You're not just copying down whatever's on the video, okay? But the first thing we have to do is we just have to investigate this a little bit. What patterns do we notice? What are we seeing? Okay, we already talked about that time won't be negative. And then it asks us for the y-intercept and then a few other questions. So I'd like you to pause the video and try B, C, D, and E. Okay, so hopefully you notice there's not a constant rate of change like there is for linear, and there's not a constant like factor. We're not just increasing at an increasing rate like we did with exponential where they were multiplying. Okay, if you'll notice, the graph seems to have the same numbers. Okay, and there's some middle points. So it looks like from 0 to 5, the graph is increasing. It stops increasing, and then it begins decreasing. Okay, and this is the behavior of quadratic functions. It may decrease first and then increase second. But if I was looking at this from a graphic standpoint, I start at 3, I continually go up, and then I come back down the same way that I went up. All right, and at the end, I don't think the fireworks are going to be going into the ground, but we put this here, just so that we see the behavior of it in our graph. So the y-intercept, hopefully we remember that the y-intercept is when x equals 0, our y-intercept is 3. What does that mean in the context of the problem? This is my initial or my starting height. This says fireworks tend to explode when they reach their highest point. When will the firework explode? So the highest point was 5 and 403. So one thing they might ask us is, like, when does it happen? That's usually a time. And that usually implies an X value. So it'll explode after 5 seconds. And how high will it be? In this case, we're talking about height, but this would be 403 feet. There could be, it could be a different scenario, but we just want to know what that X and that Y means. It says typically some debris from the exploded firework will fall back to the ground. At approximately what time do you think it will land? So we were given that the last point was 10, and then 11 would have been like way down here. So I'm hoping you estimated somewhere between 10 and 11. I don't know, 10.2, we'll say. And if you had to explain this, it's your estimate of a height of 0. All right. So all that means is for us, if we were really modeling this, okay, we would only really want to use a domain from 0 to 10.2 in this case, if I'm saying that's where it is, okay? Because the firework doesn't have like a drill on it and it starts going into the ground and we don't have any negative time. So this is our like main behavior of what a quadratic is going to look like. So if you turn the page, and I know you kind of have to flip back and forth, I'll leave it on the table. Turn the page, try and graph what this is going to look like, please. Please graph on this page from the previous, rewind a little bit. All right, so I estimated there were 4 lines between each one, so I thought of them as 25 apiece. All right, and now if we're looking at the graph of this, okay, we can see that the graph is changing from increasing from here to here. Right here technically isn't increasing or decreasing. This is where it stops. It stops at its highest point. And then the remainder of this is now decreasing back down. Okay, it is symmetric. It's symmetric around this dotted line. So if I folded it over it, it would be, it would fold onto itself. Okay, and how is this different from linear? Linear had a constant rate of change. How was it different from exponential? This was always increasing. There's exponential growth, or decreasing. Here's exponential decay. And this one had a common ratio. All right. So a lot of times in this instance, our firework is being affected by gravity. So a lot of times quadratics will mimic things that have to do with gravity. But for the most part, I think that's a good intro to what we've got going on. So I would like you to turn to the bottom of page 4. At the bottom of page 4, I think we've looked at this before. They're giving us a definition of a quadratic function. Okay, and this is our first type. All right, the highest exponent, or the should be an x squared. All right, so a can't be 0, b and c could be 0. So you could have like y equals 2x squared, or you could have y equals 3x squared minus x. All right, so you don't have to have all 3 pieces, but you definitely have to have the x squared. And this is called our quadratic in standard form. All right, and we did a lot in last unit, factoring this, adding to b, and then multiplying to c, or a times c. So we're just going to kind of start from the very basics of it now. All right, and I want you to put in your calculator f of x equals x squared, or y equals x squared, and then fill in the table from what they have for you. So pause the video, put it in your calculator. Okay, so this is what I'm looking at. Again, I'm hoping you notice a pattern here. 16, 16, 9, 9, 4, 4, 1, 1, and then it all revolves around 0. All right, so that's going to be a special point that we're going to name, but I want you to fill in our table from this. Okay, and this says, examine the patterns of change in the table. What do you notice? All right, so what I'm going to do is I'm going to figure out how much is it changing each time, and all of our increments up here, we're increasing by 1. So that's something we want to know. So that's constant on the top. And then I want to figure out, all right, what's going on here? What's 4 minus 9? Negative 5. What's 1 minus 4? Negative 3. All right, so pause and see if you can figure out what's happening there. Pause part works. Okay, so if this was linear, all of those numbers would have been the same. And this is our first round of rates of change. If I do it again, now I figure out, all right, what's happening here? To get from negative 5 to negative 3, I would need to add 2. And to get from negative 3 to negative 1, I would need to add 2. So I want you to pause and see if you can continue the second rate of change. Pause. Second rate of change. Okay. And we're noticing that the second rate of change is constant. Okay. And that would tell us, if we just had a table, that this is a quadratic function. All right. So the first rate of change was different. The second rate of change is constant. All right, so linear, the first rate of change was constant. The second rate of change is constant in this problem. All right, so I'm hoping you can see the x and the y in the note packet. You may want to highlight that a little bit, but I'd like you to graph it. And then I want you to start trying to answer some of the questions, or thinking about some of the questions that are here. Okay, so the first question asks us for the range. I drew on the graph. Here's my minimum value, and it goes up forever. So something like 0 to infinity, or y is greater than or equal to 0. Remember that greater than, we could spell the word up. Now we're going to start learning vocabulary. The turning point is another name for the vertex of a parabola, which is this point right here. Okay, and it's called turning because we're changing from decreasing and then going up to increasing. So the turning point for this would be 0, 0. I talked about the line of symmetry the last time. The line of symmetry cuts straight down the middle of this. And just so we know, this is called a parabola. The parabola will, or the line of symmetry always goes through the turning point. And in this case, it's a vertical line, so it gets x equals, and it's always the x coordinate of the turning point. Our last question that they have right now is, what is / are the x-intercepts? We only have one this time, which is rare. Typically there are 2, there could be none. But this is where we're hitting the x-axis. Not sure why that won't move. The x-intercepts are called zeros, okay? And it makes sense because this is where y equals 0. It's usually like a starting height or something of that nature. The other things that a parabola could do is it could have 2 zeros opening up. It could have 2 zeros opening down. And then it could have none. So if it didn't hit the x-axis and stayed above it, or if it didn't hit the x-axis and stay below it. Okay, but the main features are it's symmetric around a turning point or vertex, and it has an axis of symmetry. So a parabola can look like that or that. This is the graph of a quadratic function. The vertex is also known as the turning point. This is always the minimum or maximum of the graph. It's also in the middle of the pattern in the y's. Okay, so here is my vertex or turning point. Okay, and it's in the middle of that pattern. My axis of symmetry is a line when both sides of the graph are the same. And we should know that the line of symmetry right here always goes through my vertex. The zeros are another name for the x-intercepts. That would be right there and right there. The 0 part is because this is where y equals 0. And then one of the big things that they may ask us or look at is the pattern of change is that the second rate of change is constant. Excuse me. Okay, so some of the questions they're going to ask us is this a quadratic function? If it is a quadratic function, it has to have an x squared or look like a parabola. So you have two choices. You can put this into y equals, okay? Or you could expand it to see that we have the highest exponent is an x squared. All right, so the way that I investigate this, I put it into my y equals, okay? I could hit graph and see what it looks like. To me, that looks like a parabola, so I would answer yes. If I went into the table, I want to see if there's a pattern, okay? And when the numbers are really big or changing really fast, you want to go the opposite way. So for me, I kind of scrolled down and I saw that it kind of had the pattern here, 19, 19, 9, 9, 3, 3, and then 3, 1 would be my vertex. I could try and go by the rates of change. -10, -6, -2, +2, +6, +10. First rate of change is not constant. Second rate of change, add 4, add 4, add 4, add 4, add 4. So that's another way to test it. The final version is to expand it out algebraically. And if I did that, I would have to multiply x minus 3 times itself. I don't think you're ever going to be asked to do this, but you can just watch. If I double distributed here, I would have an x squared, a negative 3x, another negative 3x, and a 9. By PEMDAS, after doing an exponent, I would then distribute 2x squared minus 6x plus 18 plus 1. And finally, I could combine like terms to make that plus 19. And I could combine here to be negative 12x. Okay, and since my highest exponent is an x squared, another way of saying this is it's a second degree polynomial. I know that it is a parabola. Now, the very last thing I want you to kind of look at, and this is just a preview, is when we had y equals mx plus b, the numbers meant something. Right now, we're going to learn eventually, this is called vertex form. My vertex has the points 3, 1, and you'll notice the 3 is right there, and the 1 is right there. We're going to go more in depth with that eventually, okay? But if it says, is it quadratic, you have to figure out, does it have the highest exponent as an x squared, making it second degree? Is the second rate of change constant? Does it look like a parabola with a line of symmetry? And if we're continuing this, this would have a line of symmetry at x equals 3, and everything would be symmetric around that. Okay. So the second to last thing that I want you to try is to figure out which one of these is linear, which one is exponential, and which one is quadratic. You can put an L, an E, and a Q above the top of them. Please try so now. Pause the video. So the first one, a ninth to a third to 1 to 3 to 9. Hopefully you can see here from 1 to 3 to 9 we're multiplying by 3. That would make this one exponential. The second one, the first rate of change was not constant. But in the third one, the first rate of change was constant, making this linear. We had to go out to the second rate of change for this one. So this one is quadratic. Even though you couldn't see the symmetry of it, which isn't always going to happen in the whole, like in the whole numbers, you can go through it like that. So I'd like you to now turn to this question. I am now on page 9. All right, this is very quiz-like. So I'd like you to try and answer them. So if you could pause the video right now and answer them, great. If not, you're just going to kind of hear me go through it. So an x-intercept, I want y to equal 0. And a y-intercept, I want x to equal 0. So if I was looking at this, my x-intercept would be right here, because that's when y is 0. And my y-intercept would be right there. That's where x equals 0. Okay, so you can explain by, I meant because y equals 0, and this one is because x equals 0. Now once the turning point, all right, so we're kind of looking at our pattern. I've got -10, -4, 0, 4, back to 0. That means this will go back to -4 and then back to 10. So right here, this would be my turning point. It's in the middle of that pattern. If it wants an equation for the line of symmetry, it's always x equals, and then the value of the turning point. And then it wants to know if this parabola is a maximum or a minimum. So if I was thinking about graphing it out, and apparently I have different numbers than you. So that's 8, 3, 1, 3, 8. So this has 2 x-intercepts. And then my y-intercept is going to be 1 instead of 4. All right, my fault. That makes this point 0, 1. And we're still back to 0. So if I want to know, is this a maximum or a minimum? All right, and I'm graphing the points. I got -3, -8, -2, -3, -1, 0. This parabola is opening down, so this is a maximum. The values went increasing, stopped to decreasing. Okay, here is our last question for this. So I want you to graph it and then try and answer some of the questions, and then raise your hand to get the homework from the substitute. Okay, so if I'm putting this in my calculator, I'm looking for the pattern of the y values as I'm doing this. So we've got x squared minus 3x plus 2. And I go second graph. Okay, I'm starting to see the pattern here. 20, 20, 12, 12, 6, 6, 2, 2, 0, 0. This one doesn't show the vertex, so my vertex has to be in between 1 and 2. So that means the x-coordinate has to be at 1.5. And I'm going to show you a way of how to figure this out. So if you want to follow my keystrokes, I go second trace for calculate. First choice is 0 or value. And at the bottom, you'll see a blinking x equals. If I put 1.5 there, it'll give me the y-coordinate of the vertex. So the table gives me all the values as whole numbers for x's. That doesn't mean it has to find the vertex. So for us, we now know that the vertex is 1.5, negative 0.25. And that'll help me figure out the rest of the problem. So pause the video, see if you can answer some of these questions. Our domain is asking us if this is ever going to stop getting wider to the right and left. And the answer is no. It'll be all real numbers. My range works off the max of the min. So my min is negative 0.25, and then it's going up forever. So my range starts at negative 0.25 and goes to infinity. This says find f of negative 4. You could do negative 4 squared minus 3 times negative 4 plus 2, or you just look for it in the table. The value I got was 30. And then this asks a question where it's negative. We've had these before. It's like, where is it below the x-axis? And I think this question is really tricky because it's really only negative in this little portion right there. All right. So it hits 0 at negative 1 and 1. So in between there, it would be negative. Our vertex, excuse me, between 1 and 2, our vertex was 1.5 in the middle of that, coordinates of negative 0.25. And it asks where it's increasing. I want x values. Okay, don't give me the y values for this. So if I'm looking for increasing, right here is where it stops, and then it increases forever to the right of that. So I would accept x is greater than 1.5 or 1.5 to infinity. I'm not including the 1.5 because this is where it stops. Okay, so I know that was kind of a lot. You can always rewind or watch this video again. If that didn't excite you, I apologize. Tried to drop it like it's hot a little bit, but got confused a few times, no big deal. So we have a parabola, second rate of change is constant, line of symmetry, highest exponent is an x squared. I hope you enjoyed this. Raise your hand, get the homework. Have a great day.